whenever you're ready.
Okay, so let's go for it. So now I'm going to talk about quantum phase estimation. So why am I talking about quantum phase estimation? Well, what is it? We're going to talk about that soon. But the reason why I'm talking about this is because it's probably the most widely used technique in quantum algorithms, perhaps all quantum algorithms. So it's it's very good to know what this is. I mean, if you're interested in quantum algorithms, you should know how this works. Okay, I'll start with a setup, which is somewhat strange at first, but then we'll explain why this is a interesting setup. So the setup is that we have a unitary U, and somehow we will assume that we prepared its eigenstate. And this is the strange part. I mean, how would you actually prepare its eigenstate? It's not easy. But suppose this is somehow given to you, okay? And you know that it has an eigenvalue. Well, actually, you don't need to know what its eigenvalue is, but without loss of generality, let's say its eigenvalue is exponential I theta n. And without loss of generality, the eigenvalues of the unitaries, they must be a exponential I phase. So you're not using any generality. And quantum phase estimation is an algorithm to measure this value, theta of n. That's what it does. And quantum phase estimation serves many purposes, but in the context of quantum simulation, it mainly serves two purposes. One is for estimating ground state energy, and the other is for actually preparing ground state. So both statements may sound a bit mysterious, but we'll get to that later. For now, let's just stick with this setup and understand how this actually works. So how does this work? So if you look into this quantum phase estimation algorithm, you'll see that this really consists of two ingredients, both of which are also standard operations in quantum algorithms. One is called as the phase kickback technique, and that's quantum Fourier transform. So I'll go through them one by one. So I'd like to start with a simple example of the phase kickback. And here's a little quiz that we can think about. So suppose we have an ability to compute a function f of x, let's say on a classical computer. Then by the discussion that we had in our first lecture, we can also compute this on a quantum computer. That is to say, if we can compute f of x efficiently on a classical computer, on a quantum computer, we can calculate this, we can perform this operation efficiently. So this means addition mod 2. And we wish to somehow use this use this operation to implement this operation. So x, we want to send x, we want to apply a phase, basically. So how would we do that? I'll let you think about it for a little while. And yeah, I'll tell you the answer. So it's very easy, actually. So what you do is that you prepare this y state in a superposition state. So you choose, you begin with an initial state. this state. Okay, and then you apply precisely this operation. So when you do that, you get this now. So let's see what happens. So let's consider two cases. If f of x is 0, then this state is just that, same as the original state. If f of x is 1, then you have this state. And so you accumulate a relative phase of -1. So if you begin with a superposition state, so like this, and apply this transformation, then you get this state. And what is funny here is that this state over here, 0 minus 1 divided by square root of 2, this state is like there throughout this entire process, remain unchanged, but it does play some role. So with the help of this ancillary state, we were able to apply this phase operation. So this is a simplest example of the phase kickback. And I hope this example was completely clear, but because now I'm going to tell you about the more general version. More generally, what we would like to do is that we want to have an ability. So suppose we have an ability to implement some unitary u, and we let's say one of its eigenstate has an eigenvalue of e to the I theta, not the eigenstate, values of u. Then we want to implement this operation. So how do we do that? Again, I want to start with the simplest example. Let's say x is a single bit. So single qubit. X is a single bit, so we only have one qubit. Then I will claim that the following circuit implements what do you need? Okay. So let's just be a little more concrete. I will assume that, well, actually, let's forget about this n. So I will just call this eigenstate as theta. Okay. So theta is an eigenstate of u, and I will claim that this operation does the job. So what is this operation? So remember, in the previous lecture, we also drew some similar looking diagrams. So this was let's say this was qubit 1 and qubit 2. This was C0 from 1 and 2. And another example was this one. So this was CZ of 1 and 2. And in all these diagrams, when you have a dot, it means that this is controlling the other register. So if for the case of C0, if this qubit 1 is in the 0 state, you do nothing. If the qubit 1 is in the 1 state, then you apply a NOT operation. And here, if the qubit 1 is in the 0 state, you do nothing. If the qubit 1 is in the 1 state, then you apply the phase operation. Similarly, here, if x is 0, then you do nothing here. If x is 1, then you apply a unitary u. Okay. So obviously, if we just consider all cases, 0 theta becomes 0 theta because you're not applying anything. 1 theta gives 1 theta with a global phase. Therefore, we can see that this operation actually implements x theta to x theta with the global phase of e to the I theta x. Yeah. So is this clear for everyone? Okay. And the generalization to a larger number of integers also works. So let's say we have a 2-bit of information. So with 2-bit of information, we can represent the integer 0, 1, 2, and 3. So in the binary representation, this would be that. So let's call the first one as well, x1, and so let's refer to each of the bits as x1 and x0. Let's see. So how do we do that? We can do something similar as follows. So this diagram over here is quite similar to this diagram if we only look at the first part, but there's the second part which is different. And you can easily convince yourself, I mean, you can check for yourself that this operation actually, again, maps x theta into x theta with a global phase of e to the I theta x. The point is, if this register is in the 1 state, then, well, you apply this u twice, so you accumulate the phase twice. So you sum over all the contributions, and you get this global phase, which is actually proportional to x. And of course, generalization of this to, let's say, k bits is also very straightforward. So this is the technique known as phase kickback. The idea is that you have some unitary that you can implement on this ancillary register here. And the phase that is applied there is somehow kicked back to the register that you care about, x. And here, the theta does play some role in a sense that we are applying a unitary there. But at all times, I mean, not at all times, but before and after we apply this control unitary, this theta state is always decoupled from the rest of the system. So you can think of it as like a resource from which you can apply a specified phase. Okay, so of course, all of this can be generated from unitary transformations. So we can apply that to a general superposition state. So let's try to do that. So I would like to begin with this state. And I should emphasize that this state is very easy to make because let's say we have n qubits. Then we can simply apply this like a bunch of single qubit operators where H is again the Hadamard operator to all the qubits to actually create this state. And the reason is that if you apply H to the 0 state, this gives you 0 plus 1. So it gives you a equal superposition over the 2 bits. And this is an equal superposition over all possible numbers of size n bit. So that can be generated by simply applying H to all the qubits. So this is an extremely easy operation. So once you begin with that state and you apply the phase kickback operation, you get a phase which is proportional to x. And if you're a physicist and look at it, you can sort of see a similarity between this expression and the momentum eigenstate. So of course, not exactly the same because this is a discrete sum and the momentum eigenstate it's over a, well, it's an integral, but you can, well, I mean, this similarity is kind of uncanny. So let's see. Let's say you have your momentum of P naught. Right. So you have a momentum eigenstate corresponding to P naught, and then you just get this one. And indeed, this is a discrete analog of the momentum eigenstate. And what you can do, and if you accept that, then what you can sort of imagine doing is to change the momentum basis, change this into the momentum basis, from which you can actually extract this theta by simply measuring the wave function. And that's why is that important? Because remember, in the quantum phase estimation algorithm, our goal is to measure this unknown angle theta, because that corresponds to the that is related to the eigenvalue of this unitary U. So a natural.
Can I? Yeah, one very simple and just a naive question. So x here literally goes from 0 to 2 to the n minus 1. So when n is on the order of 10, then you already are looking at a number like 1,000 something. So
Yes,
literally,
yes.
you can implement all these integers by using the phase kickback technique in principle, right?
Yes, yeah.
I see. What about in practice? Is this something that people already know how to implement on a quantum computer?
I would say so, because I will say this. So I guess I'll talk more about this, but the circuit is very simple, no? I mean, everything is just controlled unitary. So if you have another register here, let's say x2, then you just apply control unitary 4 times and then 8 times. So obviously as n increases, the number of control unitaries that you have to implement increases. So it does get more complicated, but how to implement that, if you know how to implement control unitary, then it's very straightforward. So in that sense, yes, people know how to do this.
Okay, yeah, thank you.
But yeah, I'll talk more about this. Yeah, it's an interesting question, actually. Okay, any other questions? If not, let's get to the next slide. Okay, so quantum Fourier transform. You can think of it as the analog of the Fourier transform that you learned in first year quantum mechanics. Maps momentum basis to the position basis and vice versa. So I'm not going to go into the details on how quantum Fourier transform is actually implemented in practice, but I will say that interestingly, this can be implemented using order n square. Actually, I'm being very pessimistic here. You can even do it in order n log n steps, 1 and 2 qubit gates. And this is interesting because, let's see. So if you have an n qubit quantum state, the range of the numbers that you have is between 0 to 2 to the n minus 1. And so somehow, so if you do this, if you were to do this in a naive way, let's say using a classical computer, so suppose you have a vector indexed by 0 to 2 to the n minus 1, and you want to apply a Fourier transform, discrete Fourier transform to that, then this will take a time that is exponentially long in n, because the fast Fourier transform that we know, it scales like total number of entries in the vector times log of that thing. So the total number of entries in the vector scales exponentially with this little n. So naively, you might have expected that this would scale exponentially with little n. Actually, it only scales polynomially. So it's one of the wonders of quantum computing, but this is possible. And for our purpose, the important thing is that we can actually implement quantum Fourier transform efficiently. So when we do that, so let's remember this superposition state was initially in this form. So if you apply the inverse quantum Fourier transform, the normalization factor is, actually, I'll just write this down first. Okay, and the normalization factor is 1 over square root of n. And there's a minus sign because it's the inverse. And okay, so that's what you get. And if you sum over everything, if you just rearrange by changing the order of the sum, which is definitely possible because it's a finite sum. And you get e to the, let's see, I x theta minus 2 to the n 2 pi K. Okay, so well, whenever you see something like this, you know what to do. Like you have a phase and you're summing over this x here. So this is basically like a delta function, and its value is maximized when the thing in the exponent is as close as possible to 0. So the maximum is achieved when theta is 2 pi k divided by 2 to the n. So that means that k, the k that maximizes this, the k with the maximum probability is roughly 2 pi to the n times theta. Right. And the thing is, k must be an integer by construction. And so you can see that the larger the n is, you can get a better and better approximation for this angle theta. Okay, so that's the basic idea behind quantum phase estimation. You use a quantum phase kickback technique to somehow make a momentum eigenstate, so to speak, and then you apply the inverse quantum Fourier transform, and the component that you're likely to observe with the highest probability is very close to the this approximation of this theta with some fixed proportionality factor, which is 2 pi divided by 2 to the n. Yeah, so at least in the infinite precision limit, when the n goes to infinity, what you can see is that k actually has a exact one-to-one correspondence with the theta, the eigenvalues of u. So what it does in that case, in that limit, is that QPA quantum phase estimation performs a non-destructive measurement in the eigenbasis of u. So you have some u. Using quantum phase estimation, you can measure in this very strange basis. So it's eigenbasis of u. And of course, if you have a finite precision, like the thing that you measure is not the exact eigenvalue of u, so it'll be some approximation. So there are some subtleties there, but you can think that for all intents and purposes, QP indeed performs some approximate version of the non-destructive measurement in the eigenbasis of u. And in all of this, okay, so let's remember what we did in this quantum phase estimation. The first was obtaining this momentum eigenstate, and that used a bunch of controlled unitary. And in the second step, we used quantum Fourier transform inverse, which is just a fixed circuit which did not depend on the unitary u. So clearly, to understand how this entire procedure works, we must actually understand how the control unitary works. So how do you actually do that? So in most cases, the setup is such that we know the unitary, meaning that we have this unitary, which we can think of as a big black box. But if you look into this black box, we can actually decompose into 1 and 2 cubic gates. So, and if we know how that decomposition works out, for example, if we know if u is e to the minus IHT, where we have already implemented e to the minus IHT by the Trotter-Suzuki method, then we will be able to break down this entire unitary into these small pieces. And if that's the case, then it is very straightforward to apply controlled unit. So what you do is that you let's call it as control qubit. And if we want to implement the control version, we replace by, maybe this is not. Sorry, I think I was, can you hear me?
Yes, yes. We can hear you.
Hello? Yes, okay, sorry. I don't know when I was disconnected.
Yeah, slightly, maybe 10 seconds.
Oh, okay, I see. Right, yeah, sorry about that. So I was talking about controlled unitary, and my point was this. So we, in this quantum phase estimation business, we had two parts, preparation of momentum eigenstate and inverse quantum Fourier transform. And in the first step, we needed to apply the control unitary. And the point that I'm trying to make here is that if you know the decomposition of U, like in this diagram, then making that unitary into a controlled version is very easy. What you do is that you simply change individual gates by their controlled versions. Like this. And when you do that, you are changing, let's, for example, look at this gate. So you started with a 2-qubit gate, and by adding a control, you change that into a 3-qubit gate. And I guess for this guy, maybe a different color. For this guy, you started with a single qubit gate, but then you changed that into a 2-qubit gate because you added a control. Now, either way, you mapped a simple gate that acts on a few qubits to another simple gate that acts on a few qubits. So in the grand scheme of things, especially in the big O notation, the cost of implementing let's say the complexity of implementing U is equal to complexity of implementing controlled unitary. Okay, so what are the applications? So it was kind of a strange toy problem, as I said, because we assumed that we begin with a eigenstate of the unitary, which is in general not an easy thing to do. So one application is actually measuring the energy. So so we already established that we can actually implement e to the minus IHT efficiently on a quantum computer. And therefore, the controlled version of that can be also implemented efficiently on a quantum computer. And the precision of the energy that you can measure was inversely proportional to the 2 to the n. where n was the size of the register that you introduced to perform the quantum phase estimation. And it turns out that to compute the energy of H up to a precision of epsilon, you only need a time that scales like order 1/epsilon. It's one of the nice things about the quantum phase estimation. And this is very different from the naive approach, which would scale as order 1/epsilon square, because if you can imagine, let's say we have some generic wave function, and we want to compute an expectation value of hi. So I'm going to assume that h is a sum of local terms, and I want to compute this one term, which is certainly probably harder than measuring the energy of this entire thing. And for that thing, unless the wave function is very finely tuned, the measurement statistics of this thing will be like somewhat random. There will be some randomness. Right. So let me just first complete this part and then answer this question. So and my point is, if you have a random variable and if you want to measure its mean up to a precision of epsilon, then because of the sampling error alone, you need a complexity that scales as 1/epsilon squared. So this is a big difference between the quantum phase estimation and the energy estimation based on direct, like the measurement of the Hamiltonian. Okay, so the question was, even if the time evolution is well performed, obtain the value of h refers to the inner product of the expectation. Is this true for the expectation of h with the given time evolved state k? Is this true for the expectation? So that should be still possible. Let me think about this. The given. So I guess the easiest way is simply just apply the time evolution and measure individual eigenstates. Measure individual term of the Hamiltonian. But you could actually just apply the time evolution and then apply quantum phase estimation, and that will still also do the job.
Well, actually, if I understood the scheme correctly, then you don't have to take the inner product of the Hamiltonian operator with the state to get the energy.
You're right. Yeah, it's not like we are taking an inner product, right? So we are performing a non-destructive measurement of in this context, we are non-destructively measuring the energy eigenstates.
Yeah. But actually, I have a question because you're measuring one of the eigenstates of these, one of the eigenvalues of the unitary operator, but there are many eigenvalues of these unitary operators. So which one are you measuring? Do you know?
That's right. Yeah. So as of now, I have assumed that we begin with an eigenstate. So okay, obviously in that case, you're measuring precisely that eigenstate, but more generally, you will, yeah. Thanks for the question. That actually, this was what I was going to talk about. So in general, obviously, you will not have that. I mean, this is a very strange assumption. Like, even if you have a pure state, you in general have some portion of it. It'll be in a superposition of many different eigenstates. So you can certainly ask, in that case, what happens? And this is where my what I've been saying, which is that the point that the quantum phase estimation is in non-destructive measurement of the eigenstates becomes important. So if you somehow believe that, which you can verify later, then it's clear what's going to happen. So without loss of generality, we can assume that psi is a linear combination of the eigenstates of, let's say, a unitary. And let's moreover assume that this is minus IHT. So in this case, the eigenstates of this unitary will be precisely the eigenstates of this Hamiltonian. So if we apply a quantum phase estimation in the infinite precision limit, in the finite precision case, the story is pretty much the same. We'll measure n with probability alpha n squared. So that's all we can guarantee. So that's just a general fact. And given the systemic degeneracy, will the phase estimation work still? Yeah, great question. So if there is degeneracy, you will, let me see. Right, so yeah, this is actually an interesting question. So yeah, so let me maybe give a concrete example. So let's say we consider this example, and let's say I will denote each eigenvalues as e to the I theta 0, theta 1, theta 2. And I will assume that theta 1 is equal to theta 1, and theta 2 is not equal to theta 0. So in that case, as I said, this is still a non-destructive. What you would do is that you have a subspace spanned by 0 and 1, and its orthogonal subspace spanned by 2, so that's just one-dimensional. So I guess with probability gamma square, you measure oops, sorry, e to the I theta 2, and the post measurements after you measure, you get this state 2, and with probability, I guess 1 minus gamma square, you're going to measure e to the I theta 0, and the post measurement state is just this state but normalized. Yeah, so you basically just apply projection to that subspace. Right. Okay, so that's the general rule. And let's see. Yeah, so that's the general rule. And if you the case in which you can consider the finite correction to the when you have finite precision, that correction can be just calculated directly by, well, we have this general expression like right here, and for each measurement outcome, you can compute its let's see, compute its probability exactly, and you can also compute the post-measurement state exactly. It's not in a very nice form, but you can do it. Okay, so in general, you get that. So in practice, if you were to use quantum phase estimation to, let's say, obtain the ground state energy using this initial state, you'll have to repeat this many times, because sometimes you measure the ground state energy, but sometimes you measure something else. So when you do that, you get some histograms of eigenstates. So maybe you measured like E0, E1, E2, etc. And well, if initially you have a non-zero overlap with the ground state, then if you have enough samples, eventually you will hit the ground state. And the lowest energy that you measure, that'll be a good guess for your ground state energy. And more generally, So let's say you have measured all these energies, and then, so now you have a good idea on the distribution of the energies. Then what you do is that if you want to repair an eigenstate corresponding to this eigenvalue, you again prepare the state, apply this quantum phase estimation, and just repeat until you get this measurement outcome. Yeah. So as I said, I should mention that this there's a non-zero probability that you will fail, because unless you begin with a, let's say your goal is to measure the ground state energy. If you have non-zero overlap with the excited states, then if you apply the quantum phase estimation n times, there is still a non-zero probability that you will never measure the ground state energy, obviously. But fortunately, that probability is very small if your overlap with the ground state is decent. I mean, it doesn't have to be like very close to 1, but let's say if alpha is like 1/100, then, sorry, 1/10 or something like that, then the probability that you will never measure the ground state energy is exactly this one. So if m is larger than 100 in this case, then with high probability, you will actually indeed measure the ground state energy. Yeah. So that'll be, so an obvious application of this would be ground state preparation. So the idea is that you repeat QP many times to get a good estimate on the ground state energy, and then again apply the QP many times until you measure your guess of the ground state energy. And the upshot of this ground state preparation strategy is that it suffices to have a overlap with the ground state that is small. So like even if your overlap with the ground state is just 1%, like let's say 10 to minus 2, you still have non-zero probability of actually preparing the ground state. Actually, a better example would be that maybe you have a overlap with the ground state of 50%. So that doesn't sound great, because then 50%, you'll be in a superposition with the eigenstates, excited states, and those excited states may be very high energy. This is a possibility. But if you use quantum phase estimation, you can sort of filter out the states that have that have a lower energy. So yeah, so I guess the filtering is a good analogy, because you post-select on successfully measuring the ground state energy. So you may fail, but when you do succeed, you know you got a good representation of the ground state. Okay, so quantum phase estimation, that's what it's about. It's a very basic subroutine in Hamiltonian simulation, because it's useful for energy estimation. You can measure energy with a complexity that is better than the naive method. And you can also measure ground state. You can also use it to prepare ground states in certain setups. And the cost of the quantum phase estimation, modulo the constants, is very easy to remember. So if you want a precision of epsilon, then the cost is basically 1/epsilon times the Hamiltonian simulation cost. So whether you want to do energy estimation or ground state preparation, the best method right now is quantum phase estimation. And because that's related to the cost of Hamiltonian simulation in a very simple way, that's one of the reasons why people focus so much on Hamiltonian simulation. So I guess we'll learn more about other methods other than Trotter in the rest of the course. Okay, so that's it for today. Thanks for listening, and I'll be happy to answer questions.
I have a question. So basically, the idea to measure the energy or ground state energy is you measure the phase of time evolution operator. Am I right?
Right. Yes, that's right. Yes.
Yeah. Then my question is that in general, quantum mechanics, the ground state energy is defined up to arbitrary shift of constant value. So this constant is has no information.
That's right. Yes.
Then, for example, your Hamiltonian somehow constructed to have very large negative ground state energy rather than close to zero or something. So even in this case, you can efficiently select this large negative energy ground state.
Right. Good question. So yeah, so that is a very good question. So in practice, maybe I should tell you how people work with this in practice. So a good way to think about this is that we have some quantum spin Hamiltonian. So I will, without loss of generality, well, there will be a constant shift, but like usually we begin, let's say we have some quantum chemical Hamiltonian, we apply some transformation, and we wrote down our Hamiltonian in this way, where this P is some, I don't know, like the spin Hamiltonian, but we know exactly what this is. So then what do we do? So we could have the ground state energy can be negative, and also the phase. Also, obviously there is a redundancy modulo 2 pi, so that's another issue. So how do you deal with that? So one way to deal with this is to, let's see, basically define this new thing. Let's say H prime, which is plus, sorry, so this is not a great notation. Maybe, okay, this would be better. Let's say there are n terms. And let's say each pi are normalized operators in some sense. Then what people actually do is something like this. So they just shift the operator by shift the energy and renormalize in this way. Okay, so this newly defined Hamiltonian H prime, its eigenvalue is related to the original one by this shift. And this renormalized factor. And if you know these alpha i's, then you can compute the shift and the renormalization factor. So this way, you can always ensure that the energies are positive, non-negative, and also it's okay. Maybe there's like a factor of pi or somewhere, but you can make it smaller than 2 pi. Yeah.
I understand the idea, but in order to have this subtraction of constant, proper constant energy, I think you should know already the answer. Otherwise, how do you know how much do you want to subtract?
So like these alpha i's, these are constant. So like maybe I can go through the exact example. So let's see. Good question. So right, in this example, there will be, let's see. So there are two, let's say this is a L by L system. Then there will be total of, I believe, 2L squared such terms and also 2L squared such terms. So in this case, the thing that you would subtract would be T plus U, absolute value, times 2L squared. So this, yeah, so even without solving the problem, you can subtract this thing. Yeah.
I see.
Yeah. But having said that, this is actually important. If you, I mean, these Hamiltonians are simple enough, you can do this, but like quantum chemistry Hamiltonians, they're very complicated. And there are all sorts of different ways to subtract. And that's actually very important to like improve your scaling in practice. Because if you subtract too much, it's not good, obviously.
Yeah. But even in this case, the total energy of ground state is depending on the so-called filling factor. How many electrons do you put in the lattice system? So if you just subtract this straightforwardly, the construction you wrote down, it doesn't have any density dependence. So I think it would not work very well. No?
I guess I don't have any immediate answers, but I guess maybe one will just add the chemical potential.
Chemical potential. Oh yeah. You can, maybe you can control with the chemical potential, right? Okay. Okay.
Yeah. Okay, and there was another question, which was, right, I did not explain very well why this is 1 over epsilon squared and 1 over epsilon, but 1 over epsilon squared is actually much easier to explain. So, maybe I will do that. I'll do this in this corner. So let's say hypothetically, we measure one term in the Hamiltonian. It'll be very explicit. So maybe Pauli X operator of the first qubit. And let's say the mean, let's say we know that the mean value is 0. So that means that probability that minus one. So and measuring the expectation value, I mean, let's say we don't know that this is actually equal to 0, and we only measure this expectation value based on this measurement statistics, then what would we do? We just let's say we measure n times, then n plus is the number of times that we measured plus, and n minus is the number of times that we measured minus. So this would be the average value. And this scale, so on average, this deviates from the mean value by like, let's see, deviation is like 1 over square root of n because of the central limit theorem. So if you want to make sure that this is less than epsilon, then you need to have sample size which is larger than 1 over epsilon squared. Yeah, so that's why you get 1 over epsilon squared. For the quantum phase estimation, you get 1 over epsilon because I skipped that part very quickly. Right. So in quantum phase estimation, the the dominant cost of the quantum phase estimation is 2 to the n times the cost of implementing and control unitary. And the precision that you get, so this is the key formula. So theta is 2 pi k divided by 2 to the n. So the relative precision is roughly like k is just an integer number. So the smallest unit here is 2 pi divided by 2 to the n. So in that sense, the precision is 1 over 2 to the n. So So I guess the main point is this is epsilon, and let's say we apply this operation n times, then this is n. So this is 1 over n, roughly speaking. Yeah. Okay. Then can we say that QP is generally superior to the variation of quantum eigensolver in the search determination of eigenvalue of a given Hamiltonian? So whether QPA is better than variation of quantum eigensolver or not depends on a lot of details. So I think for quantum chemistry Hamiltonians, where there's no nice structure, you have these four-body interaction terms all over the place. In that case, yeah, QP is definitely better than variation of quantum eigensolvers. But for variation of quantum eigensolvers, there are like nice methods to measure like many observables at the same time. So there may be a regime in which variation of quantum eigensolver is better, assuming that you have the exact eigenstate. So when it comes down to the measuring energy, if you don't have the exact energy eigenstate, then it's more hard to say, because QPE, you can actually filter out the exact energy eigenstate, whereas variation of quantum eigensolver, maybe it could be faster in some settings, but maybe the result that you get is not accurate. Let's see. I guess I believe the video of today's talk will be was recorded. So
yeah, as to the video record, I think Professor Jong-won Han is recording, and also our center is recording, and we plan to upload this video record usually on our center's YouTube, APCTP YouTube. And also, I think we plan to upload this recorded video file on our center's homepage. So it will take some days, but be patient.
Okay. Okay. So if there's no further question, yeah, I just have a very important announcement. The next lecture is not this Friday. It will be on Wednesday, 1 week from today. So be sure to put that on your calendar. And before leaving, let's say a word of thanks to Professor Kim, who gave a very excellent set of lectures today. So thank you. Thank you very much. See you.